In this video, we're going to look at basic algebraic proof. In order to prove something, we need to construct a logical argument that will hold true for all values. We can't just pick isolated cases with numbers and show that it works for those. We need to show that it holds true for all cases. To begin with, we're going to look at some of the basic terminology used, and then we're going to go on and answer some questions. So in the question, if we see the word sum, that means that we're going to add. If we see the word difference, that means that we're going to be subtracting. If we see the word product, we're going to be multiplying. So sum, difference and product. Add, subtract, multiply. If we see the word integer, we know that that is going to be a whole number. So 2, 5, 10 and so on and so forth. If we see consecutive numbers, so jotting this down, consecutive numbers follow each other. So if I look at some consecutive integers, we could have 6, 7 and 8. If I looked at consecutive even numbers, we might have 10, 12 and 14. Consecutive odd numbers, 3, 5, 7 and 9. So these now are consecutive. We need to be happy with odd and even numbers and positive and negative numbers. What I'm going to do is introduce the idea of letting n be equal to some integer. So if we now let n, and just jot in here, let n be equal to a whole number. What we can say is the following. If we look at even numbers, we can say that even numbers will be 2n. If we multiply any number by 2, we're going to end up with an even number. If we look at odd numbers, we can either write these as 2n plus 1, or we can write these now as 2n minus 1. So if you just think now, anything even we can multiply by 2, so if we add 1 or subtract 1, we're going to end up with odd numbers. So we'll probably use this in a few of the different cases. So let n be equal to an integer. An even integer will be 2n, an odd integer will be 2n plus 1 or 2n minus 1. So let's look at the first question. We're asked to prove that the sum of any three consecutive integers is always a multiple of 3. So let's start off with the words sum, consecutive, integers, and we're looking at a multiple of 3. Sometimes the question might say divisible by 3. It really doesn't matter. We can show it anyhow. So if I wrote now consecutive integers, we might have 1, 2 and 3. If I added those, 1 plus 2 plus 3 is going to give me 6. 6 now is a multiple of 3, so 6 is a multiple. So writing this in, 6 is a multiple of 3. That is not a proof. It's just showing it holds true for that particular case. What I'm going to do is construct my proof. I'm going to say let n be equal to an integer. So n is some integer. If we now look at consecutive integers, I've got two choices. I could either go for now the following. I could go for n plus 1 and n plus 2. And just think about that sensibly. 5 plus 1, 5 plus 2, 5, 6 and 7. Or I could write n minus 1. I could have n as my middle number and n plus 1 as the third number. I often choose this particular route as it sometimes makes the algebra easier. It doesn't always make it easier, but it might do. So let's go ahead now and sum these. So we'll have the sum. Taking the sum, we've got n minus 1 plus the n plus 1. So if I collect the n's, I've got 3n minus 1 plus the 1. The plus 1 and minus 1 will cancel, 3n, which is a multiple of 3. So 3n, which is a multiple of 3. So a multiple of 3. And I'm going to conclude now with the statement, therefore, the sum now, and I'm just repeating the question, the sum of any three consecutive integers, three consecutive, so consecutive integers is always a multiple of 3. So integers is always a multiple of 3. And that's my proof concluded, multiple of 3. So all I've done is simply let n be equal to some integer. So consecutive integers, n minus 1, n and n plus 1. I've shown that when I sum them, which means I add, we can simplify to 3n, which is a multiple of 3. Therefore, the sum of any 3 consecutive integers is always a multiple of 3. Of course, if you went for that approach, if we went for the first ones, it's perfectly fine. N plus 1 plus n plus 2. That's going to give me 3n plus 3, which we could write factoring as 3n plus 1, which is also a multiple of 3. Just think about this. Anything that we can factor a 3 out is either a multiple or divisible by 3. So that gives us now our if we use this one, another approach. Okay, we're asked to prove that if the difference of two numbers is 4, then the difference of their squares is a multiple of 8. So we've got now the difference, we've got the difference, we've got the squares, and we have now a multiple of 8. So what we're going to do then is the following. So let n be equal to some number. Okay, so now I have a difference of 4. So if we look now, difference of 4, so difference of 4, what I'm going to have is n minus 4, and we're going to have n. So these have a difference of 4. I could write n and n minus 4, but for this particular proof, I'm going to use this square first. So we're now looking at the difference of their squares. So I've defined the numbers, the number n, and then the difference between them is 4, so n and n minus 4. You can, of course, do n plus 4. So if we now look at the squares, so what we've got then are the squares. So the squares will be n minus 4 all squared, and we'll have n squared. So they're the squares. Now if we look at the difference of the squares, so jotting this down, we're going to have n minus 4, which we need to square, and we're going to subtract n squared. Setting this up as an identity, I can use the 3 lines. It holds true for all values. Expanding the first bracket, n squared minus 4n minus another 4n plus 16 minus the n squared. We can tidy this up. The n squareds will cancel, and I'm going to write this as 16 minus 8n. You can write it as minus 8n plus 16. I want to show that it's a multiple of 8. I can factor 8 out here, and I have 2 minus n, and I can state which is a multiple. So which is a multiple. So multiple of 8. I'm then going to say therefore, and I'm going to conclude using the question mark here. If the difference of two numbers is 4, then the difference of their squares is a multiple of 8. And I'm just simply going to write that. I won't do it in this particular case, as we saw how long it took me on the last one, but I would conclude now by writing that out. Let's look at another one. We're asked to prove that the quantity 3n plus 1 all squared minus the quantity 3n minus 1 all squared is a multiple of 6 for all positive integer values of n. So this one is slightly easier as it's guiding us. So all I'm going to do is expand this bracket. That's going to give me 9n squared plus 3n plus another 3n plus 1. I'm then going to subtract away from this now the expansion of 3n minus 1 all squared. So 9n squared minus 3n minus another 3n plus 1. So if we look at this, what we've got is 9n squared plus 6n plus 1 minus the 9n squared. We've got here minus 6n, so we're going to be adding that, and then we're going to be subtracting the 1. We can see from here now that this one will cancel with this one. This one will cancel with this one. So we end up now with 6n plus 6n, which is going to give me now on here, let's just write that in white. What we have is 12n, and I'm going to simply write this now as 6 lots of 2n, which is a multiple of 6. So which is a multiple of 6. So multiple of 6, and just jotting it down, therefore, and then I'm simply going to write out now the statement that I was given. So at multiple of 6, we can show that we can take out this factor of 6. Let's look at another one. We need to prove that the quantity n plus 1 all squared minus n minus 1 all squared plus 4 is always even for positive integer values of n. So if we expand this, we're going to have now n squared plus n plus n plus 1 minus now, and if I expand this one right here, I can use square brackets or curly brackets, n squared we're going to have now minus n minus another n plus 1, and then we're going to have plus 4. So this is going to give me n squared plus 2n plus 1 minus n squared. This is going to give me minus 2n, so we add that plus 2n minus the 1 plus the 4. So if we look, we can see the n squareds are going to cancel, the 1's are going to cancel. We've got 2n plus 4. So let's write this in. So we can say that this is going to be 4n plus 4. We can factor this to 4n plus 1, which is, so just writing this down, which is always even, which is always even, so always even as a multiple of 4, as a multiple of 4. So multiple of 4. If we multiply anything by 4, we're going to get an even number. So therefore, just concluding my statement, I'm going to write the question back. You could write that that's going to be 2 lots of 2n plus 2 if you wanted. So an alternative would be to say 2 lots of 2n plus 2, which we know anything multiplied by 2 is going to always be even. I prefer that particular approach, as we know 4 times anything will always be even. Okay, next one, prove that n plus 1 all squared minus n minus 1 all squared plus 1 is always odd for all positive integer values of n. So expanding the brackets, n squared plus 2n plus 1 minus, and then the curly bracket this time, or round bracket I should say rather than curly bracket, n squared minus 2n plus 1 plus 1. So we're going to have n squared plus the 2n plus 1 minus n squared plus 2n minus 1 plus 1. So if we look to cancel off, we've got the n squareds cancelling. We're going to have now the plus 1 and the minus 1. So what we have is the following. So we have 4n plus 1. We can say now that 4n is always even. So 4n is always even. Therefore, it's always even. Therefore, now 4n plus 1 is always odd. So it's always, so just jotting this down, is always odd. Therefore, now just concluding my statement, I'm going to write now this particular statement that they've given me to conclude. So quite a nice little question, and we've concluded it like so. We're asked to prove algebraically that the sum of the squares of any two consecutive numbers always leaves a remainder of 1 when divided by 4. So if we look now at the following, let n be equal to a number, so n is equal to a number, we have now two consecutive numbers. So two consecutive numbers, we will have now the consecutive numbers, so consecutive numbers, I'm going to have n, and then I'll have n plus 1. You can of course have n and n minus 1. So we're looking at the squares, we're looking at the sum, and we're looking at a remainder of 1 when divided by 4. So let's go ahead now and look at the squares. So what we've got then are the squares. So if I just jot this down, we're going to have n squared and we're going to have n plus 1 all squared. If we sum the squares, we can see that we're going to have n squared plus, expanding the bracket, n squared plus n plus 1. If we now consider tidying this up, what we're going to have is the following. We can say that this is going to be 2n squared plus 2n, and then we're going to have plus 1. So we want to show that when this now is divided by 4, there is a remainder of 1. So with this one, what I'm going to do is factor this part right here. All I'm going to do is leave the 1 out here, and I'm going to take out now 4. That's going to leave me now 1/2 n squared plus we're going to have 1/2 n, and we're going to have plus 1. We can say now that 4 lots of 1/2 n squared plus 1/2 n is divisible by 4. So divisible by 4, so divisible by 4. Therefore, now this statement right here has a remainder of 1. So now let's put that 1/2 n squared plus 1/2, and then we're going to have n plus 1 leaves a remainder of 4. So leaves leaves a remainder of 1 when divided by 4. Leaves a remainder of 1 when divided by 4. So when divided by 4, and I conclude with my statement in the question. So with that one, slightly more challenging, but if we take out this factor now of 4, and then we're left with 1 over, we can say it can be divided by 4. If you don't like this particular approach in terms of taking a half out, what we could do now is let n, so just writing this here, let n be equal to 2n, for example, or let the number, let's write this here, let 2n be equal to the number. So if we wanted to make our algebra easier, consecutive numbers now, so consecutive numbers, we would have the following. We would have 2n, and we would have 2n plus 1. So if we look at the squares, we're going to have 2n, which we need to square, and we're going to add to that now 2n plus 1 all squared. So with this one, what I'd have now is 4n squared plus 4n squared plus 2n plus 2n plus 1, which is going to give me on here 8n squared, and then we're going to have on here plus 4n plus 1. So if I wrote that, I could write this now as 4, then we'd have now 2n squared plus n. So all I've done in that particular case now, let's go ahead and check that works. That looks fine. We could write this now as 4 lots of, on here, 2n squared plus 2n plus 1, which is probably easier to see, if you like, as a multiple or divisible by 4, leaving a remainder of 1. It's entirely up to you on how you want to view that. We can see using n or 2n will give us the same result. Okay, let's try another one. We're asked to prove algebraically that the difference between the squares of any 2 consecutive even numbers is always a multiple of 4. So we've now got consecutive even numbers. So if we look at those, so even, and I'll just jot this down, consecutive even numbers. So what we can have then is 2n. We need to be careful here. Next one is going to be 2n plus 2. A common error is to write 2n plus 1. We must define these even numbers as 2n and 2n plus 1. Simply letting it be equal to n doesn't confirm that it is an even number. If we think about this, if I have consecutive even numbers, 4, 6, 8, it's going up by 2 each time. So we need to be adding 2, hence why I've done that. So we need to find now the difference, their squares, and we've got our consecutive even numbers. So it's going to be a multiple of 4. So what I'm going to do is the following. I'm going to take now the squares, so let's look at the squares. And I like to work now with taking the 2n plus 2 first. So we're going to have 2n plus 2, which we're going to square, and we're going to have 2n, which we're going to square. It just makes now the algebra slightly easier. So if we look at the difference, what we're going to have is the following. Expanding that bracket, 4n squared plus 4n plus another 4n plus 4, and then we're going to subtract from that now the 2n squared, which is going to give me 4n squared. We can see from here now that the 4n squared and the 4n squared are going to cancel. We got 1 plus and 1 minus, so we can write this now as 8n plus 4. We need to show that this is always a multiple of 4, so taking the 4 out, that leaves me 2n plus 1, which is a multiple, so which is a multiple of 4, so which is a multiple of 4, and we can therefore conclude with the statement from the question to finish the proof. Let's finish off with one more, and on this one it says prove algebraically that the sum of the squares of any three consecutive even numbers is always a multiple of 4. So with this one we want now three consecutive even numbers. So if I had now, let's put this on, so consec, we're going to have consecutive even numbers, and this is where I'm going to use the algebraic skills to help me out. So we'll have 2n, we will have 2n minus 2, and we'll have now 2n plus 2. So these are three consecutive even numbers. So what we're going to do now is sum the squares. So I'll find the squares, I'll sum them, and then we'll show it's a multiple of 4. So what we're going to have then is 2n minus 2 squared. We're going to have plus 2n, which we need to square, and we're going to add to that now 2n plus 2, which we need to square. Now with this one, what you could have done is 2n plus 2 and 2n plus 4. I think this is going to work out slightly nicer. 4n squared minus 4n minus another 4n plus 4 plus the 4n squared. Now expanding this one, plus the 4n squared plus 4n plus another 4n plus 4. So if we look at what's going to cancel from here, we've got the minus 4n, the minus 4n, the plus 4n and the plus 4n. So this leaves me now in total, I've got 4n squared plus 4n squared plus 4n squared, which gives me 12n squared, plus 4, which is plus 8. So we can factor this, taking out the factor of 4, we can have 3n squared plus 2, which is a multiple of 4. So which is a multiple of 4, and we're going to write therefore, and we'll just conclude our statement. So that one's done, all sorted, and we've done it with that particular approach. I think we've got one more that we could look at, so let's have a go at one more. We're asked to prove algebraically that the difference between the squares of any two consecutive odd numbers is always a multiple of 8. So if we look at our consecutive odd numbers, we could go, so consecutive odd numbers, we could say that one of them was 2n plus 1 and the next one was 2n plus 3. Instead, what I'm going to have is 2n minus 1 and 2n plus 1. Just think about this. This is going to make our algebra easier on this particular example. So just think now, if n, let's just say n was equal to, let's say 4, we could say 2n minus 1 was 7, 2n plus 1 is 9. We can see that these are consecutive odd numbers. So we're now looking at the squares. So what I'm going to have, the squares, we're going to have 2n minus 1, which we need to square, and we're going to have 2n plus 1, which we need to square. So we're looking at the difference, so jotting this down, the difference, expanding this bracket, 4n squared minus 4n, then we're going to have minus another 4n plus 1. We're going to subtract away now the expansion of this one, which is 4n squared. So let's put this on, 4n squared. We're going to have now plus 4n. We're going to have now plus another 4n. And then we're going to have plus 1. So we need to show that this is a multiple now of 8. So if we look at this, what we're going to have is 4n squared minus 8n plus 1 minus the 4n squared minus 8n, so minus 8n, and then we're going to have minus 1. This is going to give me now the 4n squareds are going to cancel, so let's just do those. So 4n squareds are going to cancel, the plus 1 and the minus 1 cancel, which leaves me now minus 16n. We need to show that this is a multiple of 8, and we can write this now as 8 lots of minus 2n, which is, so just jotting this down, which is a multiple, so multiple of 8. You can of course do it the other way around. If you want, you can do your 2n plus the 1 first, and it might make the algebra slightly neater. and I just conclude with my statement, therefore, and repeating the question. So if you do it the other way around, you won't have this negative 16. It doesn't really matter. Either way round, we can show it's a multiple of 8, and we conclude with the statement. So there we go. That's an introduction to basic algebraic proof.